In this video, we're going to look at another example of trig substitution. This one will be more difficult because we have to complete the square so that we can put the integrand into a pattern that can be done by trig substitution. So what we have is minus x squared plus 2x. That is what we have inside the radical. So let's factor out negative 1. Negative 1 times x squared minus 2x. Now the key here is to take this minus 2 divided by 2 and square it. Negative 1 squared is 1. So now we add and subtract. Plus 1 minus 1. So let's rewrite this. Now we get negative 1 times x squared minus 2x plus 1. Negative 1 times negative 1 gives us plus 1. So what we have is minus 1 times, but this part is a perfect square. So that's going to be x minus 1 all squared plus 1. So what we have shown through completing the square is root of 2x minus x squared can be rewritten in this form. Root of 1 minus x minus 1 squared. Now we can see that this is the right pattern for trig substitution. So if we have root of a squared minus u squared, constant squared minus variable squared, we make the transformation u is equal to a sine theta. Differentiate both sides, we get du is equal to derivative of sine is cosine. Du is a cos theta d theta. So what we have is root of 1 squared minus x minus 1 squared. So we have constant squared minus variable squared. The constant is 1 and the variable is x minus 1. So x minus 1 is equal to 1 sine theta. Differentiate both sides, we get dx is equal to cos theta d theta. Alright, so what we have shown is the integral root 2x minus x squared dx. We completed the square and we have integral root of 1 squared minus x minus 1 squared dx. And we're now going to apply trig substitution. X minus 1 equals sine theta. And differentiate dx is cos theta d theta. So let's rewrite the integrand so that we get everything in terms of the angle theta. 1 squared minus x minus 1 squared. That's equal to root of 1 minus x minus 1 is sine theta, so we get sine theta all squared. Now we have a trig identity. Cos squared theta plus sine squared theta is 1. That means 1 minus sine squared theta is cosine squared theta. So we get root of cos squared theta, which is absolute value of cos theta. But because of the way we restrict the angle theta, we can drop the absolute value and write this as cos theta. So the integral root of 1 minus x minus 1 squared dx, and that's going to be a trig integral, cosine theta times cos theta d theta. This part is root of 1 minus x minus 1 squared. This part, cos theta d theta, this part is dx. We now have a trig integral that we can solve. So we have integral cosine squared theta d theta. And that is always the strategy when you're given a quadratic integral, something that's hard to integrate. Your goal is to apply trig substitution, get rid of the radical expression, and turn it into a trig integral so that we can solve it. And we have the tools to do that. So we're now going to apply the trig identity. Cos squared theta is 1/2 times 1 plus cos 2 theta. That's 1/2. 1 plus cos 2 theta d theta. 1/2 is a constant. We can bring it right outside the integral. We get 1/2. And let's integrate term by term, splitting up the integrals. What is the integral of 1? That's just theta. What is the integral of cos 2 theta? Well, integral of cos theta would be sine theta. But we have cosine 2 theta. So we have to apply U substitution. Let U equals 2 theta. The U is 2 d theta. So to make a long story short, integral of cos 2 theta will be sine 2 theta divide by 2. Don't forget to divide by 2. That's reversing the chain rule or doing a U substitution. Plus C. Alright, so what we have is we've shown that the integral root 2x minus x squared dx is equal to 1/2 times theta plus sine 2 theta divided by 2 plus c. Let's simplify this. We get 1/2 times theta plus, we have a trig identity, another trig identity, sine 2 theta is 2 sine theta cos theta. That's going to be 2 sine theta cos theta divided by 2. Plus the 2's cancel out, and what we get is 1/2 theta plus 1/2 sine theta cos theta plus c. Now we can't just stop there because we have to get the answer in terms of x. So let's do that. The trig substitution that we applied was x minus 1 is equal to sine theta. Take the inverse sine of both sides, and we get theta is equal to arc sine minus 1 of x minus 1. Sine theta is equal to x minus 1 divided by 1. That's equal to opposite over hypotenuse. So we can now create our reference triangle. Let's do that. What we have is a triangle, 90 degrees, and here's the angle theta. Sine theta is opposite, that's x minus 1. Over hypotenuse, this is 1. Now we can calculate the missing side by applying Pythagoras. The missing side would be root of 1 squared minus x minus 1 squared. This is a reference triangle that allows us to get the answer back in terms of x. So let's put this in a box. Alright, let's label it. This is the reference triangle. Alright, so we have sine theta is x minus 1 over 1. What about cos theta? Cos theta, well, we need cos theta because we have cos theta here. So cos theta is adjacent, which is going to be root of 1 minus x minus 1 squared divided by hypotenuse. This is 1. That's adjacent divided by hypotenuse. Alright, so what we have shown is the integral root of 2x minus x squared dx is equal to 1/2 theta plus 1/2 sine theta cos theta plus c. And we created a reference triangle, and we now have all of these. We have theta in terms of x, we have sine theta in terms of x, cos theta in terms of x, so we can get our result back in terms of x. That's equal to 1/2 times theta, that's sine minus 1 of x minus 1, plus 1/2 times sine theta, that is x minus 1, times cos theta is root of 1 minus x minus 1 squared, plus c. That is the answer. We also applied some trig identities, so we applied sine squared theta plus cos squared theta equals 1. We applied a half angle identity, cos squared theta is 1/2 times 1 plus cosine 2 theta. And so it's really important to memorize these identities so that you can apply them when a need arises. Here we have sine 2 theta, the last identity we applied. Sine 2 theta is 2 sine theta cos theta, that's a double angle identity. Alright, thanks.